Monday is the last class, and I'll do a semi-formal review of the whole semester on Monday. But today, well, we've completed all the topics that I laid out. At least, you know, I've said what I wanted to say about them all. And rather than bring in one additional topic, perhaps, of my own choosing, just because, I think it hopefully be more valuable to you all. Stick with what we've got, or things that you're interested in. So if you can think of anything goes here, in effect. Things that I've talked about, my topics and concepts, things that I've left you confused about, bring them back. Or objects I've talked about but haven't, you know, there are pieces you want to hear about, let me know. And if they're just other random stuff, ask me. So this is your choice, open choice, or whatever. If you want, yeah. P and N type semiconductors again. So if you remember, a semiconductor is basically an insulator, and in forming an insulator, if you assemble, and most of these things are crystal materials, very orderly systems, and when you bring together atoms of the same element, a whole slew of them, and organize them in a crystal, how the electrons settle into quantum levels, these quantum standing waves in the material, makes a huge difference. And in a semiconductor, the crystal reaches electrical neutrality just as it finishes filling a group of quantum standing waves, a group of levels. And if there were one more electron that needed to go somewhere, it couldn't go into that group of levels since they're all full, and according to the Fermi Pauli exclusion principle, you can't keep sticking them in. So the next one would have to go into what's called the conduction levels, which energetically are significantly higher in energy. So the next electron would be costly energetically. Okay, that's a pure semiconductor, a pure insulator, where you've just filled the band completely. I guess I can resurrect this slide out of there. If, however, so that's this. Of course I hit the wrong button. Come here, guys. So you've got all the valence levels are filled with electrons, and none of the conduction levels are filled with electrons. And this assumes there's not much extra energy around. So at lower temperatures, if you go high temperatures, or you throw in bright ultraviolet light, for example, you're going to have electrons moving between those levels, and you will start to have conduction. But anyway, it's an insulator. So far, so good. To make a P or an N type semiconductor, you introduce impurities. And what the impurities do is suppose you take, for example, did I do it again? I was once again playing with my laser pointer on my desk and didn't put it back in my collection. Anyhow, if you take a couple of the atoms that are in here, this assumes that every atom is the same, and so you might imagine they're all silicon atoms. Suppose you take out one of the silicon atoms and replace it with aluminum. Aluminum's got one less electron than silicon. It's got one less positive charge, and therefore it's got one less negative charge. So the crystal still forms, and it's still structurally almost identical, except it doesn't really want quite as many electrons. It wants one fewer electrons than it used to. And as a result, it will reach electrical neutrality when one of those valence bands levels is empty, or it has only one electron rather than two. And that now is a P-type semiconductor. It's chemically doped, they call it, so that it doesn't want quite as many electrons as are necessary to fill the valence band. And it now is electrically conducting because there's that one empty spot can move around. Yeah, it's sort of associated with the aluminum, the single interloper aluminum atom, but actually it can move around, and it moves around by having a nearby electron jump into fill that quantum standing wave and leave a new empty spot, which then has another electron jump into it. So is this okay with P-type? Is that okay with everybody? What's the other alternative? Put in an atom that has one additional electron, one extra positive charge, therefore it wants one additional electron. And after silicon, I think comes phosphorus. I'll get rusty on the periodic chart. But if you put a phosphorus atom in there instead of a silicon atom, now you've got an atom that needs one more electron to reach electrical neutrality. The crystal forms the same way. The band forms the same way. Very subtle, negligible changes. It needs that extra electron. Where's the electron going to go? It goes into the only available standing wave for it in the conduction level. So now you've got one electron in the conduction level. And it, again, is an electrical conductor because if you apply an electric field, that one electron sitting in the standing wave can migrate. And you can pull it through the material. Okay? So P-type semiconductors they're not a pure semiconductor. They've been doctored so that they have some empty spots in the valence band. And N-types have been doctored chemically so that they have some electrons in the conduction band. Okay? And that's the N-type and P-type as created chemically. You can play with the populations of electrons in the levels by external effects like electric fields. And that was the case for the MOSFET, the MOSFET. If you put a lot of positive charge near a region that's chemically supposed to be P-type, but if you put a lot of positive charge there, you can draw extra electrons into that region. And you put a lot of positive charge nearby. You draw electrons into the region, and although it's chemically supposed to be P-type, it fills all the valence levels, so it's not P-type anymore. In fact, you can bring electrons all the way into the conduction levels. And now it behaves as an N-type material. So it's chemically P-type, but it's electrically forced to be N-type. Any questions further about this stuff? Where is this relevant? This is done, all your electronic gadgets have had this sort of thing happen. They often will start with pure semiconductor. They will inject other atoms in as a vapor, as ions, shoot them in. The ways in which they doctor the crystals so that they end up with N-type or P-type, that's not my expertise, but they do this. Or they grow them right out of vapor, for example, where the vapor is mostly silicon bearing gas, but they put a little bit of phosphorus bearing gas or a little bit of aluminum bearing gas, and they chemically shift things a little bit. All right? Other questions about this? Other questions about anything? Yeah. How does this apply to the MOSFET transistor? When you assemble a MOSFET transistor, at least conceptually, in reality it's built very, very complicated process of forming these tiny little structures. The MOSFET transistor is constructed out of three pieces of doped semiconductor, at least. I mean, in its simplest form, it's got three regions. The two end regions are one type of semiconductor, and the middle is the opposite type. And there's all kinds of recipes for doing this, and how extensively you dope them is important. So you can go everything from not doping them at all, in which case you've got a pure semiconductor, to heavily doped, in which case it's almost like a metal. It just conducts electricity so nicely. Anyhow, so one of the simplest MOSFETs is composed of two pieces of N-type semiconductor with a channel made of P-type semiconductor in between. And I think the idea is also you make the P-type semiconductor just barely P-type, not very much, just a little bit. Okay? And when that assembly is complete, and you can think of it as touching the pieces together, although they're built together, it doesn't really make any difference. When that assembly is complete, the attraction, the opportunity to give up energy is just too compelling for the electrons in the N-type material. In the N-type ends, there are electrons in the conduction band. band. That's what N-type means, right? So they're sitting there in the conduction band at both ends. And here in the middle is stuff that was chemically made P-type, so it had some empty spots in the valence band chemically. And the opportunity for these nearby electrons that are sitting right at the edge of the P-type material to move spatially and then thereby give up energy by dropping into the lower energy standing waves is just too compelling, and they do this. There's a cost to doing it. Because they do it, they leave behind the positive charge that made this N-type material N-type. It's got extra positive charge in it. That's why it ended up with extra electrons. So having electrons leave, the positive charge says, wait a second, you're leaving me behind, come back, come back. So that costs energy for them to migrate out of there. But the energy that's released in letting them settle into the empty valence levels exceeds that energy. So they settle. So anyway, you end up with this whole region between the two ends that doesn't conduct electricity because it no longer has those empty valence levels that P-type material is supposed to have. They've been filled in by electrons that wandered in and got stuck. And the conduction band never had any electrons, so it's there. So anyway, you get this whole central region is called the depletion region because it just doesn't conduct electricity. Any questions so far about this? The cool thing though is that you can make it allow it to conduct electricity by playing with the electric charge on the gate. If you put positive charge on that gate, it attracts more electrons into the middle region. That makes it energetically favorable for them to get closer to that positive charge. They want to do it, so they migrate in, and they end up in the only available levels that can handle them, because the valence is filled. They end up in the conduction band, and it becomes the whole conduction band now has extra electrons in it, and they can move. And so the MOSFET has switched from being effectively pure semiconductor, the previous slide, to being effectively all N-type, one big chunk of N-type material that conducts electricity pretty well. And so you have these this is called an N-channel MOSFET just because when it's conducting electricity, the channel behaves as though it's N-type. It's chemically made P-type, but that doesn't matter. It's been switched by the positive charge. And I mean, this is everywhere, all these gadgets. So if you think of it, those of you who did some of the Orion questions will have encountered an old question I wrote about cell phones. A lot of gadgets still do this. Cell phones now are sort of always on, but there were days, there was an era when your gadgets were truly off a lot of the time, and you pressed a button to get them to come on. And they might turn themselves off spontaneously after you leave them alone for a while. But anyway, when you pressed the button, what did you do? You somehow sort of forced a new behavior where the battery is now connected in a circuit with the gadget. What was the switch that went from being off to being on? It's an electric switch because it wasn't really the button you pushed. And what it is a MOSFET. So a lot of gadgets have one big power MOSFET in there, one that can handle the entire power for the entire gadget. And they turn the gadget on, or someone turns the gadget on by putting positive charge on an N-channel MOSFET. You put the charge on there and then you just leave it. It'll just sit there for a long time. And it turns on this device without no mechanical movement has gone from being an electrical insulator to an electrical conductor. Okay? Other question? Next. Why is the weather so nice outside? Yeah. You're all comfortable with electric power distribution, transformers? Yeah. Okay. Okay, so the interference effects with lasers and the diffraction effects with lasers. When you have a laser beam, it's a single wave, which makes it particularly easy to see strange wave effects with it. And the wave effects show up in every case. They're always there with light, for example, but they're often hard to see because you've got lots of different waves, and the interference of the cool effects that affect one wave are washed away by all the other waves. So, okay, so if you're using a laser and you send it through an obstacle course, some of the things that happen. If you send it through two slits, so some of these are famous experiments. You send it through two slits, and the beam, the wave goes along and goes through those two slits. The parts of the wave that make it out the far end now continue on. They are still pieces of the same wave. They have the same character to them. They're the same frequency and wavelength and all that. And they propagate along. And if you look off in the distance and you go look for where is the wave strongest and weakest, it isn't the sort of simple geometry effect you might expect. You might expect that if you put two slits on there, send the wave through, that you're just going to end up with two bright shadows, the opposite of shadows, and nothing else. That's not what happens at all. You end up with this funny pattern, and the pattern comes about because of interference effects. When the light goes through those two slits, it continues on, and like the ripples, there are a lot of famous pictures of this. So if you send a water wave through a narrow gap, the ripple spreads out in a circular pattern, leaving as it goes beyond. Let me see if I can find one of those. I bet I can find. Turn off some of these lights up here, spots. So what you're seeing up there is sort of a single water wave that was coming along here, passing through two slits. So the wave can only continue here, and it can continue here, and off it goes. And it doesn't just go out when it goes through those two gaps. It can't just travel as just this ripple of water traveling in a straight line with sharp edges. Waves don't do that. They don't have sharp edges like that. Instead, it gets wider, and it gets broader and broader. It travels out as these spherical ripples, or cylindrical, not even that, circular ripples that spread out. And in the region where those ripples begin to overlap, you're getting interference effects, where if this is on waterways, but it's the same with light, if you get crests from both of these outgoing circular patterns, if the crests coincide, you get a strong wave there. It's going up and down a lot. If the crest of one and the trough of the other coincide, you get nothing. They cancel each other. And you can see these effects in real life in water. You see them when you go to the beach and watch water going past breakwaters and stuff like that. The waves get all messed up as they travel through there, and they tend to travel out as these circular patterns. The same thing happens with light. So if you send a single laser beam through two slits, one up high, one down low, you get this spherical. It's not spherical, although the words have come out because this is like graduate school. They go out as these patterns. They are technically spherical shells that go out. But anyway, when they overlap, you get some regions in which you get constructive interference and some where you get destructive interference. And the pattern is much richer than you would expect from just sort of geometry. Two bright lines. Nuh-uh, you don't get two bright lines. You get this whole pattern. In fact, it's brightest right in the middle, right where the two lines, right between the two slits, where classically there should be no light at all. Is that okay so far? The other effect that's strange is the diffraction effect. Let me see, light diffraction. Diffraction. Learn how to spell. Gotta find some diffraction patterns. Too complicated. This over here, incidentally, is the two-slit diffraction pattern. This is what I was just describing, where it was brightest right in the middle. If you send two slits, if you send light through two slits, classically, this right between in the middle should be black, should be dark. It's not. It's brightest. It's that peak intensity. So it's a completely non-classical result. Let's go back to where are these. Can I find a diffraction pattern? This is one. That's if you take, and this is white light, which is strange. How do they make? It's very hard to make this kind of pattern for white light. In fact, I don't even know whether I want to use it. This is more the pattern you get for if you take the wave. If you take a laser beam and you send it through a very, very narrow pinhole, narrow on the order of the wavelength of the light. And you truncate off the rest of the wave. So you're allowing only a tiny piece of the wave go by. You're imposing sharp edges on that wave. And this can't last. Waves don't like sharp edges. So it begins to spread. And how to understand the spread, it happens for many reasons. There are many ways to think about it. And I think I've used more than one in this class. One of them is that in order to keep the laser beam narrow, it needs to be able to use interference. It needs all the pieces of that wave in order to get interference that is constructive right on center and near on center, and destructive everywhere else. If you chop off most of the wave, and all it's got to work with is a little bit, it can't maintain that those interference effects. It's no longer able to get nice destructive interference outside of beam center. And consequently, it can't stay narrow. It gets wide. It spreads. And the other thing is that if you try to localize anything too much, a wave structure too much, you can localize it for one moment, but subsequently it's going to spread like crazy because you have taken control. You've forced it to define its position, and position and momentum are conjugate variables. They go opposite one another in the Heisenberg uncertainty principle. If you pin down position too much of one of these waves, the momentum gets undefined. And the momentum, in this case, you're pinning it down in this plane to this area. That means the momentum in this plane gets completely out of control, and it goes off in directions in this plane very, very rapidly. And so the light does that. It spreads as it travels forward. You've lost this momentum, you've lost control of momentum in this direction by narrowing it down. The consequences of diffraction, where do you see this? I told you that, well, we would certainly see it with lasers, but it's of consequence, particularly to people who work with telescopes. In order to get very, very high resolution imaging, the Hubble telescope gets these amazing pictures of tiniest details. In part, that's because it's outside the Earth's atmosphere, and the Earth's atmosphere has all kinds of refraction problems. Remember refraction? It's not a perfectly homogeneous medium to look through. It's got complications, little patches that are hotter than others and colder. The wind going through, it's not uniform, and the result is the speed of light isn't uniform, and you get tiny bendings, little refractions in the atmosphere, which are a nightmare for astronomers, light-based visual astronomers. So go out of the atmosphere. Great. So you got the Hubble out there. Having a big mirror is nice because it collects lots of light. This is an issue we talked about with cameras. But the other thing about it is that having a big opening on the telescope doesn't truncate the wave very much. So each of these waves that have been working their way across space and come into the telescope, as soon as you block parts of it, which you do by having only a limited aperture on the telescope, or by having structures in front of the telescope, in this case mirror, like the imaging devices are sitting out there in front of the, it's a mirror, so the light has to go through those imaging devices, and they truncate part of the wave. That causes diffraction effects. That you lose a little bit of the control of which way that wave was heading, and it spreads, and so you can't get perfect light from a distant star. Should be coming, for all practical purposes, from a truly a point source. The star is so small out there in the distance that it's got no size from our perspective here on Earth. At least a distant, yeah. So it's you should be able to image it right down to a tiniest spot on the image sensor, but you can't because of the diffraction effects that happen because your aperture isn't big enough, or there's stuff in front of the lens. Okay? I give the long stories. It's in my nature. Other questions? Yeah, Christine? How the rainbow works? Yeah. So to remind you the various effects with light as it travels through matter. Sunlight. In empty space, all light travels at one speed altogether. It travels, of course, as a wave, so the wave stuff is interesting, but it's there. Once light enters the atmosphere, it no longer travels completely the same. I'll get to this in a second. It begins to slow down as it's playing. The matter is playing with it. Basically, it's causing charge to jiggle back and forth, and that process of affecting the electric charge in the air delays the propagation of the wave a little bit. So the refractive index of just ordinary air is not quite 1 being full speed. It's a little above 1, which means it slows down. The refractive index is just defined as the factor by which light slows down. So 1 is no slowdown. 1.0001, air has, I think, 4 zeros in it, but I can't remember for sure. It's just a little slowed down. That depends a little bit on the air. If the air is hot and therefore the molecules are spread out more, it's not as physically dense. It has fewer molecules per cubic meter. It slows light down a little less. And this is why you get refractive index effects in the air. You've watched light traveling over a hot burner on a stove or something like that, or you can see the ripples of heat ripples. This is familiar to people, the distorted view of the world beyond. That's refraction going on because the light is going through it's going through air, it's all air, but the air isn't uniform, and its refractive index is varying. And you see the light being bent as it's trying to go through. You don't see reflections so much, but you see the bending effects. You do see the reflections when light comes in at a shallow angle and hits hot air and speeds up. And then you get total internal reflection. That's the mirage effect. I mean, this literally is the mirage effect. So if you've ever been out in the desert or in a really flat road out in a really sunny environment, you can see the sky reflected, total internal reflection off that hot layer. Okay? Heading towards rainbows, though. So refraction occurs whenever light changes speed at an interface or transition between materials. It also undergoes reflection at those transitions. So when light enters something fairly abruptly, it goes into water, for example. For a rainbow, it does two things. It reflects to some extent. The bigger the change in speed, the more the reflection. And it refracts, except if it's going straight in. If it's going right in perpendicular to the surface, it goes right in. But otherwise, it refracts. Its direction of travel inside the material is different from what it was outside. And for slowing down, it bends toward the perpendicular. For speeding up, it bends away from the perpendicular. All right. those effects are all a little bit dependent on the frequency of the light. The blue light, in general, for transparent materials, blue light travels more slowly than red light. And you might wonder why, and I've had discussions with people about, why does the blue light travel slower? Well, it turns out that it's because all transparent materials are not transparent everywhere. They're transparent in the visible, sure, but they're not transparent in the ultraviolet. They have resonances in the ultraviolet, meaning they're radiated transitions. If you send in the right ultraviolet light, the material will absorb it. Glass, diamond, all the plastics. Ultimately they will absorb the ultraviolet light, particularly in certain frequencies. And that absorption involves a very serious interaction between the light and the material. And as visible light, a wave of visible light is traveling through the material, and it's encountering the same structures that would absorb ultraviolet, begin to look at that light when it first arrives, and they go, ooh, is this ultraviolet? Is this my favorite frequency, at which I'll go crazy? And they begin to play with it initially, because when you first see the wave, imagine you are that structure, and you first see the edge of that wave coming in, you can't tell what its frequency is. You've only seen one tiny piece of the front end of the wave, that first rise in electric field. You do not know what frequency it is yet. You have to watch it for a while and go, oh no, it's not my favorite. So there is an initial plane. These potentially absorbing structures play with every wave that goes by to see, is it their favorite, the one they're going to absorb, and if not, they let it go. But the playing process delays the wave a little bit, and the longer the playing process goes on, obviously I'm simplifying things significantly. It's okay. The longer that playing process goes on, the more delay there is. And the blue waves are closer to these ultraviolet absorptions than the red waves. So the blue waves get played with longer before the material goes, nope, I can't absorb this. And the result is the blue goes slower. And the blue will go slower still if their absorption is just outside the visible. And they're really just on the edge between ultraviolet and violet. The blue will slow down a lot. And therefore that light will go, white light will get seriously spread out in time. Random thing to bring up. This affects camera lenses. Camera lenses struggle with the fact that different colors of light travel at different speeds, because, and this is relevant to rainbows, that also means that the bending of light depends on the frequency of light. Blue light bends more in refracting than does red light. Is that okay? Any questions about why that happens? Blue light slows down more, it bends more. That's unpleasant for color photography. So they work like crazy to compensate for it, and they do by and large. But the fanciest of the lenses are often made with exotic transparent materials that have ultraviolet resonances so far out in the ultraviolet that blue light is way away from them. And the red light and the blue light both travel almost the same speed. So they are low dispersion glasses. Dispersion is this effect of handling the different colors differently. And the very expensive camera lenses that you can buy, like the L series lenses, for some reason they're called L's often. Maybe that's for low dispersion. They are often made with fluorite materials and they may even be crystalline optics. They may not be glasses at all. And they handle the colors better because all the colors travel nearly the same speed. Okay? Reel it back into rainbows. The rainbows make use of all these effects: refraction, reflection, and dispersion. That is the frequency dependence of the speed at which light travels through material. And for the classic rainbow, and there's more than one kind of rainbow, and I hope all of you have seen things like double rainbows. There's a second rainbow. If you get really lucky, you see the first rainbow, and then around it, there's a second rainbow out there. The rainbow happens typically early in the day or late in the day, because you don't want the sun overhead. You want it over your shoulder. So it's coming along over your shoulder, through, obviously it's got to get, no clouds there, but clouds and rain over here. And the light from the sun hits those raindrops, which are spherical. Again, contrary to the drawing of raindrops as tears. They're not, they're just spheres. And they're coming down. And when light hits those spheres, as shown in this drawing, one of many paths it can take through the droplet. The one that's responsible for the classic rainbow involves the portion of light that enters the droplet high and enters it and undergoes refraction in the process, bounces off the back, and exits it undergoing refraction in the process again. So it's a pretty simple path. And the other rainbows, and people have actually studied this. You can imagine that they've gone hog wild looking at all the crazy paths light can take through the droplets. This particular path catches a good fraction of the light entering the raindrop, participates. It separates the reds and the violets nicely. The violets, being higher in frequency, travel slower, they bend more. So they bend more on entry and they bend more on exit, and those two bends don't compensate for one another. They actually enhance one another. So the violet light coming out of these droplets is aimed higher than the red light. The red light is aimed lower. So when you look up at the sky and see the light from those droplets, well, you don't see the violet light from the low droplets goes over your head. The violet light from the high droplets goes over your head. The violet light from the low droplets finally reaches you. But the red light, since it doesn't bend as harshly, comes down at you more, and you see it higher in the sky. You see light. You see the droplets that are sending red light out higher in the sky. Is that okay? So, and it's circular because really, it's at a certain angle relative to the axis that's formed by the sun, your head. That defines a line. That's the center of this rotational axis, and the rainbow follows is at a certain angle away from on that axis. Here's the angle opening up. It's at this angle. It doesn't matter where it is relative to the angle, but it's where it is relative to the axis, as long as it's at that right angle, the correct angle relative to the axis. So if you see rainbows when you're in a plane, which you can see them, you can see them not as an arc, because there's no ground to block the bottom. It's an entire circle. Also hope you've seen that. The rainbows that happen. You can see rainbows when sunlight hits the clouds and does this rainbow trick. Clouds are just little water droplets too. So it's rain that's not falling in effect. Yeah. What about reflection and dispersion? So, the reflection here. Yeah, I did short shrift of the reflection effect. When light changes speed, or any wave changes speed, part of it reflects. And the bigger the change in speed, the more the reflection is. So you get reflection of water waves. You've seen those too when the water hits a dock or something like that, and changes speed, it comes sailing out backwards. When sound hits the wall, it echoes. Same thing. In this case, when light hits the back of the raindrop and tries to exit, something like 3 or 4% of it reflect. There are other reflections here, but they're not interesting to this particular rainbow. There is, for example, about 4% reflection as light tries to enter the raindrop. There's also about 4% reflection as light tries to leave the raindrop. Neither of those is interesting for the rainbow. They're there, but I didn't draw them. This reflection is crucial. That reflection is the light failing to leave. 3 or 4% of the light fails to leave the raindrop, continues inside the raindrop, and ultimately comes out and reaches your eye. But you can see that because you've only got about 4% of the light coming out, and it's separated into the colors, rainbows are faint. It's not in your, sometimes they're pretty bright, but they're never like looking at the sun, because it's fractions of fractions of fractions of the light that come back to your eyes. Am I okay? Or more questions of this? The dispersion part, again, is just this effect that light travels at different speeds according to frequency. And the blue light typically goes slower. And that dispersion affects, where does it show up in real life? It is responsible for this color separation because refraction itself becomes color dependent. Because different colors of light slow down by different amounts, they bend by different amounts when they undergo refraction. So this is how the rainbow gets its colors. It's how a diamond has colored sparkles. It's why camera lenses have to struggle to deal with all the colors the same way and form images that have the colors under control, because dispersion is a nuisance for them, for camera lenses. Dispersion is also a nuisance for information transmission. For example, in fiber optics, if the different frequencies travel at different speeds in a fiber optic, the information that you're trying to convey on that, on light in the fiber optic, gets slurped out in time, because if the red parts of the transmission travel faster than the blue parts, and there inevitably are a spread of frequencies in the transmission because of the fact that you're winking on and off, you're manipulating a light wave, and that means it no longer has a pure frequency anymore. It's got a spread in frequency. Therefore, it does have a red end and a blue end of the spectrum involved in the transmission. And if the red end goes faster than the blue end, what started as sort of tightly controlled pulses of light, perhaps, gets smeared out into slurps of light. And that spoils your ability to send information as fast as you would like. So this is a big deal. For example, trying to send the internet across the Atlantic Ocean to Europe. Dispersion is a major problem for them. Have I done justice to dispersion at this point? Okay. Other questions? All right. It being Friday, thanks for coming. See you on Monday.